Rigging can be described as the planned movement of a load using various types of rigging equipment. Rigging jobs can range from light lifting operations, in which simple hoisting mechanisms are used, to complex or heavy lifting procedures, in which the load is heavy, bulky, or hard to balance. As with any rigging operation, to safely perform a complex or heavy rigging job, you have to be able to select the proper equipment and inspect the equipment for damage. You also need to be able to interpret lifting capacity charts, evaluate equipment stability and load balancing considerations, and properly plan and carry out a rigging job. Safely completing a rigging job involves identifying and selecting the proper hardware and equipment. Also, since rigging components are subject to wear and damage, you have to inspect the components before they're used. Any component that's damaged or defective should be removed from service and destroyed. One piece of hardware that's used to connect different pieces of rigging equipment is a shackle. Two common types of shackles are anchor shackles and chain shackles. Shackles used in heavy lifting jobs typically have a much higher load capacity than those used for lighter lifting jobs. The safe working load limit of a shackle is marked on the shackle body. As with all rigging components, shackles are designed with a safety factor or design factor built in. The design factor is basically the ratio between the load or tension at which a piece of rigging equipment will fail and the actual load on the equipment. As a general rule, the design factor for rigging equipment should be no less than 5:1. Using a design factor ensures that a shackle rated at 52 tons will, under normal circumstances, lift 52 tons. Hooks are common rigging components that can be used in a variety of applications. For example, cranes typically have one or more hooks for lifting loads, and many slings have hooks for connecting loads to a lifting device. The way a hook is attached to a rigging line depends on the design of the hook. For example, this hook has an eye through which a wire rope line is connected. Other hooks use a clevis as a connection point. And some hooks have a swivel that allows them to rotate without tangling the connecting lines. Hooks typically have their safe working load limit stamped on them. The safe working load limit of a hook is the weight that the hook will safely handle. Many hooks have a safety latch to prevent a load from slipping off. Hooks that don't have safety latches should be secured to close off the opening to the hook's throat. One method for securing the throat of a hook is called mousing. Mousing involves wrapping wire or fiber rope across the hook's throat to prevent connectors from slipping off the hook. When wire rope is used to lift a load, the wire rope tends to stretch and untwist. When the load is lowered, the rope tends to contract and twist in the opposite direction. To help prevent a wire rope from transferring its normal twisting motion to the load being lifted, some type of swivel is often used. All cranes rated at 10 tons or more, as well as most smaller cranes, have a swivel built into the crane hook. But swivels are also available as separate components. Turnbuckles are used to make small adjustments in the length or the tension of a wire rope or a chain. For example, turnbuckles can be used to adjust the lengths of sling legs so that the lifting hook can be positioned directly above a load's center of gravity. A turnbuckle consists of two threaded rods that screw into a single body. One rod has right-hand threads, and the other one has left-hand threads. By rotating the body of the turnbuckle, the distance between the ends of the rods can be shortened or lengthened. Turnbuckles commonly have jaw, hook, or eye ends. These ends can be used in any combination. The safe working load limit of a turnbuckle is based on the diameter of the threaded rods and on the types of ends being used. Rigging links and equalizer plates are connectors used for specific purposes. Both components have holes that can vary in size and location, depending on the need. Typically, rigging links have 2 holes, while equalizer plates have 3 or more holes. Equalizer plates can be used to level loads when the sling legs are of unequal length. Before any type of rigging link or equalizer plate is used, it's important to carefully inspect the component for wear and cracks. Some pieces of equipment come with lifting connectors already attached to specific points. One such connector is a lifting lug. Lifting lugs are typically welded, bolted, or pinned to the object being lifted. They're located so that the load will be safely supported and balanced when it's lifted. Another type of lifting connector is an eye bolt. 2 basic types of eye bolts are plain or shoulderless eye bolts and shoulder-type eye bolts. Spreader beams and lifting beams are devices used on large, bulky loads when ordinary slings can't be used alone. A spreader beam changes a rigging configuration from an angled lift to a straight vertical lift. This helps balance large loads and prevents the rigging from damaging the object being lifted. A lifting beam is similar to a spreader beam. The main difference is that with a lifting beam, the lift is typically made from one point on the beam. The lifting beam increases the number of lifting points, or pick points, from 1 to 2 or more. This helps balance the load and keep it from sliding, tipping, or bending. Before a spreader beam or a lifting beam is used, it should be inspected to ensure that it isn't cracked, worn, bent, or twisted. A tag line is a rope that's used to help prevent a load from swaying or spinning during a lift and to help guide the load to its final position. Every lift must be controlled with 1 or more tag lines. The rigging foreman is responsible for determining the number, size, and length of the tag lines to use during a rigging job. To ensure that tag lines are in good condition, riggers should inspect them periodically for wear and damage. Different types of cranes can be used to move heavy loads from one place to another. The specific type that's used can depend on factors such as the location of the load, the terrain of the land around the load, and how the load is to be moved. In this part of the program, we'll focus on cranes that have overhead girders or trusses that travel on rails. We'll refer to these cranes as bridge cranes. Although there are different types of bridge cranes, most of them share some common features. For that reason, we'll focus on one particular type of bridge crane for our discussion. We'll examine the basic features of a cab-operated overhead crane. Here's the crane we'll use. Unlike many overhead cranes, this one is used outside. From this view, we can see the major components of the crane. Here's the crane's bridge. The bridge travels on elevated rails that extend from one end of a storage area to the other. A trolley is mounted onto the bridge. It carries a hoist mechanism which is used to lift a load. The trolley and hoist travel back and forth on the bridge. The bridge and trolley arrangement enables the crane to move a load in 2 horizontal dimensions. An operator's cab moves along the bridge with the trolley and the hoist mechanism. Overhead cranes are equipped with main start and stop buttons to help prevent accidental startup of the crane. Before any of the crane's controls will function, the start button must be pushed. The operator can then use the control levers to operate the crane as needed. Once the operator finishes using the crane, he can use the stop button to deactivate the controls. The bridge control is used to move the crane's bridge along the elevated rails that run the length of the storage area. It's a variable speed control with a forward and reverse direction. Moving the control lever in the forward direction causes the bridge to move forward along the rails. Moving the lever in the reverse direction causes the bridge to move backward along the rails. On some overhead cranes, an automatic brake mechanism stops the bridge movement whenever the bridge control lever is released. The trolley control is used to move the trolley along the crane's bridge. This variable speed control has a left and right direction. By moving the control lever to the left and the right, the operator can move the trolley back and forth across the width of the storage area. Some overhead cranes have an automatic brake mechanism that stops the movement of the trolley whenever the trolley control lever is released. The hoist control is used to activate the crane's lifting mechanism. This control has a down and an up direction. Moving the control lever in the down direction allows the operator to lower a load. Moving the lever in the up direction enables the operator to raise the load. A brake mechanism locks the hoist to prevent the load from dropping whenever the hoist control lever is released. The swivel hook control is used to rotate the crane's hook. By using the left and right buttons of the swivel hook control, the operator can swivel the load hook so that a load can be rotated to the left or the right. Many overhead cranes are floor controlled. That is, their controls are mounted on a pendant. A pendant is a control box suspended from a cable that's attached to the electrical system of the bridge. When a pendant control is used, the crane operator walks along with the load as the trolley or the bridge travels. One thing to keep in mind if you're using a pendant control is to not activate two buttons for a single feature simultaneously. For example, attempting to move the bridge in the forward and reverse directions at the same time could damage the crane's control mechanism. Nearly all mobile cranes, as well as some stationary cranes, are equipped with some type of boom. A boom supports the lifting tackle and can be swung, tilted, and in some cases extended and retracted to a desired position. Some boom cranes have telescoping booms, which are controlled by hydraulic cylinders powered by pumps. Others have lattice booms, which are controlled by cables that are driven by winches. But regardless of how a boom crane is configured, its mobility and versatility makes it suitable for a wide variety of rigging jobs. Since we can't look at every type of boom crane that's available, we'll focus instead on the basic features of one type that's commonly used to move heavy loads, a crawler crane. Because of its wide crawler tracks, a crawler crane is very stable on soft or rough terrain. As with most crawler cranes, this one has a lattice-type main boom. The base of the main boom is hinged to the superstructure of the crane. On this crane, the opposite end, or top, of the main boom has an extension called a luffing jib. The luffing jib provides additional boom length and supports the lifting tackle. Extending downward from the ends of the main boom and the luffing jib are fixed-length wire ropes called pendant lines. The jib pendant lines are supported at the top of the main boom by a pair of structures called front and rear struts. From the top of the boom, the main boom pendant lines and the jib pendant lines connect to a movable support structure called a mast. The mast also provides a connection point for the boom hoist lines. The boom hoist lines are threaded or reeved around sheaves and drums on a structural frame called a gantry. The network of hoist lines and support lines makes it possible to raise and lower the main boom, the luffing jib, and the load. Devices called boom stops limit the angle of the main boom at its highest recommended position. A device with a similar function, called a jib backstop, prevents the luffing jib from toppling over backward. Counterweights mounted onto the back of the crane supplement the crane's weight and offset the weight of the load. An operator's cab houses the crane's controls. Many modern cranes have a computer that provides valuable information about operating conditions. For example, when this crane is started up, its computer goes through a system test. It prompts the operator to respond to various safety and operating messages in a startup checklist. Once the startup checks are complete, the operator enters information into the computer about the crane's configuration. The computer then uses that data to calculate and display information, such as the amount of weight on the load line, the operating radius of the crane, the luffing jib offset angle, and the maximum lifting capacity that's available under the current conditions. This is the crane's swing control. After releasing the swing brake, the operator can move the swing control forward or backward to move the revolving part of the crane and the boom to the left or the right. This is the crane's main boom tilt control, or simply the main boom control. By moving this control forward or backward, the operator can change the angle of the main boom, that is, lower or raise the top of the boom. Here's the crane's main hoist control. It's located beside an auxiliary hoist control, which isn't being used in this crane. By moving the main hoist control forward or backward, the operator can lower or raise the crane's main hoist line. This is the crane's jib tilt control. By moving this control lever forward or backward, the operator can change the angle of the luffing jib, that is, lower or raise the end of the jib. Cranes typically have foot pedals to help control basic operating functions. For example, this crane has a brake pedal for the main hoist and a brake pedal for the auxiliary hoist. Both hoists have automatic braking systems as well. This crane also has pedals to control the left and right crawler tracks, and a throttle control pedal for the engine. By law, all cranes must undergo safety inspections. The frequency and thoroughness of these inspections depend on factors such as how the crane is used and how much it's used. Inspection guidelines are based on federal regulations issued by the Occupational Safety and Health Administration, or OSHA. Guidelines that apply to overhead cranes and gantry cranes are collected in one category, and those that apply to crawler cranes, locomotive cranes, and truck-mounted cranes are collected in another category. The procedures outlined in each category are further divided by the type of inspection that's required. For instance, inspection procedures for cranes in regular service are divided into two basic groups: frequent inspections, which are general inspections typically done by the crane operator at least once a day, and periodic inspections, which are thorough inspections commonly done by an expert at least once a year. An overhead crane should undergo a general inspection at least once a day, or ideally before each shift. Much of this inspection involves visually checking the crane's major components. For example, the bridge, trolley, and hoist mechanism should be checked for obvious wear and damage. Not all of the components of an overhead crane are clearly visible from the ground. Some must be inspected from up near the operator's cab. Among these components are the reels for the wire rope and electrical lines, as well as the lines and connectors that make up the lifting tackle. All these components should be visually inspected for wear, damage, and improper reeving. It's also important to check the operating controls in the cab to make sure that they're functioning properly. Only after all these basic checks have been completed should the crane be placed in service. The frequent inspection of a crawler crane is basically a visual check of all the crane's major structures and systems. For example, before this crawler crane is used, the operator does a walk-around inspection to make sure that the major components, such as the crawler tracks and all the safety guards and plates, are in good condition. He also checks for any broken or loose connectors around the crane's superstructure. Because of its importance, the operator keeps a close eye on the crane's hydraulic system during the inspection. Part of checking the hydraulic system involves making sure that the fluid level is normal. Another part involves checking hydraulic lines for leaks or other problems. It's also important to inspect the crane's support structures and hoisting components, including the wire rope, the reels and sheaves, and any connectors that may be present. The operator completes the inspection by checking the crane's computer and operating controls to make sure that they are working properly. In this topic, we examined heavy lifting hardware and different types of bridge cranes and boom cranes. We also looked at some basic crane inspection checks. Now try some practice questions on this material. Before you can safely perform a lift, you have to be able to read and interpret the load capacity charts for the crane you're using. Capacity charts explain critical measurements and warnings that must be considered when lifting capacities are calculated. Crane manufacturers provide individual capacity charts for each machine they produce. These charts can't be interchanged because similar cranes can still vary a great deal depending on how they're equipped. To prevent accidents and equipment damage, the proper capacity charts must be used, and all the requirements listed on the charts must be met. The chart heading lists basic information about the crane and its equipment. On this chart, the information includes the manufacturer's name and the model of the crane. It also includes the boom number and the style of the boom point, or top, the length of the crawler tracks, and the weight of the counterweight. The information in the chart heading should be compared with the equipment on the crane to make sure that the chart and the crane match. The lifting capacities section of the chart is actually two parts, one in text form and the other one in the form of tables. The text part helps clarify some of the capacity information that appears in the tables. The tables, which are arranged in columns and subdivided based on the boom length, provide the actual capacity values for the crane under different equipment configurations and operating conditions. For example, this part of the table shows capacity information for a main boom length of 70 feet. The columns provide information about the operating radius of the crane in feet, the boom angle in degrees, the boom point elevation in feet, the crane's capacity in pounds with the crawlers retracted, and the crane's capacity with the crawlers extended. Capacities listed in the shaded area are based on the strength of the structural parts of the machine. Capacities followed by the letter B indicate boom positions in which there's too little backward stability, that is, too little resistance to overturning backward. Using this line from the chart, we can see that with an operating radius of 30 feet, a boom angle of just over 68 degrees, and a boom point elevation of 72 feet, the crane has a lifting capacity with the crawlers retracted of 142,800 pounds, or with the crawlers extended of 165,400 pounds. The lifting capacities section of the chart is actually two parts, one in the form of tables and the other one in text form. The text part helps clarify some of the capacity information that appears in the tables. The tables are arranged in columns and subdivided based on the boom length. They provide the actual capacity values for the crane under different equipment configurations. For example, this part of the table shows capacity information for a main boom length of 70 feet. The columns provide information about the operating radius of the crane in feet, the boom angle in degrees, the boom point elevation in feet, the crane's capacity in pounds with the crawlers retracted, and the crane's capacity with the crawlers extended. Capacities listed in the shaded area are based on the strength of the structural parts of the machine. Capacities followed by the letter B indicate boom positions in which there's too little backward stability, that is, too little resistance to overturning backward. Using this line from the chart, we can see that with an operating radius of 30 feet, a boom angle of just over 68 degrees, and a boom point elevation of 72 feet, the crane has a lifting capacity with the crawlers retracted of 142,800 pounds, or with the crawlers extended of 165,400 pounds. The operating conditions section explains the conditions that affect the crane's lifting capacities. For example, this section of the chart indicates that the crane must be operated in a level position on a firm surface. If the crane is operated in an unlevel position, the boom will be subjected to high side loads that could damage the boom or tip the crane. The machine should be leveled to within 1% of grade. One way to check a crane's level is to place a bubble level on the superstructure near the rotating mechanism or turntable. Another way is to check the crane's level gauge if it's equipped with one. The operating radius section describes the horizontal distance from the center line of the crane's rotation to the center of a vertical hoist line or load block. This measurement is taken with the load freely suspended. We can use this illustration to show operating radius measurements for this crane. One measurement extends from the center of the crane's rotation to the center of the main load line. This is the main load line operating radius. Another measurement extends from the center of the crane's rotation to the center of the whip line or auxiliary hoist line. It's the whip line operating radius. A third measurement extends from the center of the crane's rotation to the center of the jib line. This is the jib line operating radius. The operating radius section of the chart also includes information about the crane's boom angle. The boom angle is the angle between the horizontal plane and the center line of the lower or base boom section. The angle of the crane's boom directly affects the operating radius, and the operating radius directly affects the crane's lifting capacity. The boom point elevation is the vertical distance from ground level to the center line of the main boom point shaft. This illustration shows the boom point elevation for a crawler crane. Any up and down movement of the boom, that is, any change in the boom angle, will directly affect the boom point elevation as well as the crane's lifting capacity. The machine equipment section provides a more detailed accounting of the crane's equipment. For example, here we see that the crane's total counterweight of 122,400 pounds consists of 3 separate counterweights that range from 39,000 pounds to nearly 42,000 pounds. The chart instructions for reeving the main load block must be followed to ensure that the proper number of line parts are used. Each maximum load value listed on the chart should be greater than or equal to the maximum capacity that will be required for the lift. The corresponding number of line parts must be used for the maximum load selected. That number is based on the catalog breaking strength of the rope with a recommended safety factor. The load line and whip line specifications apply to the wire rope that's used for the main hoist and the auxiliary hoist. These specifications must be met before the capacity chart can be used. This part of the capacity chart provides information about the maximum boom and jib lengths that can be lifted unassisted. These 3 blocks provide that information based on different crane positions and boom lengths. Never attempt to raise a boom or a jib that's longer than what's allowed under the conditions specified on the chart. The lifting capacity of a machine changes when different styles of boom tips are used or when a jib is added. A jib deduction block on the chart lists the number of pounds to be deducted from the lifting capacity when the jib is attached. The deduction varies with the length of the jib. Different booms can be used on a crane and different jib combinations can be used with each boom. The load charts that come with a crane include jib lifting capacities charts. In order for a jib capacity chart to be used, all the requirements listed on it, as well as those on the main boom capacity charts, must be met. Here's an example of a jib lifting capacity chart. As the chart heading indicates, the chart applies to a particular type of jib used under specific conditions. One of those conditions has to do with the jib offset angle. The jib offset angle is the angle from the center line of the main boom's top section to the center line of the jib. The jib offset angle must be known before a jib capacity chart can be used. An important consideration during any rigging job is making sure that the load is properly balanced. Load balancing involves equalizing the weight of the load at various lifting points. Distributing the load's weight in this manner helps prevent the load from bending, breaking, or falling. Load balancing techniques can vary depending on the load and how it's being moved. Extremely heavy and odd-shaped objects often require multiple lifting points or pick points to spread the load and avoid overloading one point. These types of loads often require the use of special rigging equipment such as spreader beams and lifting beams. In some cases, equipment comes with lifting connectors such as lifting lugs or eye bolts already attached to specific locations to help ensure a balanced lift. Load balancing can also be affected by sling location. Slings must be properly positioned to prevent overloading a lift point or damaging the object being lifted. Extreme caution must be used with slings because unknown stresses can develop during a lift if the load shifts or is bounced around. Small changes in the sling angle can greatly affect a sling's capacity. Because of these uncertainties, a safety factor of at least 5 to 1 must be used for all rigging components. During any rigging job, the primary concern is safety. In order to safely accomplish a rigging job, some basic questions must be answered, including who is in charge? What is the job to be done? Where will the work be done? And when will the work be done? We can get a better idea of how these questions are answered by watching a heavy rigging job. These two workers have to move this load to another location on their company's yard. The first thing they do is meet to discuss who's in charge of what and to look over the load. During the meeting, they discuss where the load will be moved, when it will be moved, and how best to rig the load. They also determine the weight of the load. In this case, the load has a data plate, which indicates a weight of just over 30,000 pounds. Once they've established some basic guidelines, the workers are ready to get started. The rigger on the ground selects the equipment for the job based on the weight of the load and how the load will be rigged. As he selects the equipment, he inspects each piece for wear or damage. At the same time, the crane operator checks the capacity charts to make sure that the crane is of adequate capacity to handle the load. Then the rigger directs the crane operator to position the load hook and slings directly above the center of the load. He then attaches the rigging equipment to the load. With the necessary connections made, the rigger signals the crane operator to test lift the load a few inches. Once the rigger is confident that the load is secure and properly balanced, he signals the crane operator to start moving the load to its destination. Along the way, the rigger and the crane operator are careful to watch for personnel in the area and for obstructions such as overhead power lines. When the load is directly above its appointed destination, it's slowly lowered into place. To complete the job, the rigger disconnects the lifting lines, signals the crane operator to move the lifting hook out of the way, and returns the rigging equipment to its proper storage place.